Yeah, I own a small business designing and producing my own goods, primarily using 3D printing technologies. So I'm here to help you take your project from your brain into a nice print. Yeah, so this presentation is broken up into three rough parts. We have a basic overview of 3D printing and how 3D printing works. A little bit of like general design features, so something you might find in kind of any product that you would want to produce, and then some 3D printing specific features that are basically the 3D printing technology allows you to make some stuff that you can't do through any other manufacturing technology. And I kind of assume some level of CAD and 3D modeling understanding. Um, so hopefully you have a basic understanding. If not, hopefully you still get something out of it. But yeah, overview of 3D printing. So the way that 3D printing works is that your model is converted from the nice, beautiful model into discrete sliced layers, and then the print is made layer by layer. So it has a couple effects. You can kind of get this stair-stepping as your model, the approximation of your model is made through the layers. And then you also run into a big thing with 3D prints is they have anisotropic part properties, which basically just means that the strength and other things are not the same in all directions. So prints are much more likely to have a failure at along the layer lines. So if you have something long like this, if you printed it vertically so that the layer lines go across, it's much more likely that that part will break than if it was printed horizontally with the layer lines running through the part. So you get a much stronger part in this orientation. In general, there's a ton of different material options. I'm not going to talk too much about them today. It's up to you to sort of investigate what your project is and what material works the best. However, you can find that there are glass or carbon fiber additives in some of the materials, which change it doesn't increase the print strength, but it helps with stiffness and durability of parts. You still have that layer line separation issue, even with those. And then in general, when 3D printing, the more engineering focused a material is, the more complications you can run into when 3D printing with that. Yeah, slicing is a very critical part of 3D printing, and that's how that model goes from a 3D model into something that the 3D printer can actually produce. And so there's a number of parts in there that are very important. So you can kind of see in this image here, this is the layer lines. So each discrete layer of the print is usually a set height. You have the perimeters, is the outer walls that this kind of orange and yellow that goes around the perimeter of the print. This is where most of the strength of your part comes from. You have the infill, which is this kind of squiggly section, and this is just to help fill in the volume of the print, but generally doesn't add too much strength. You have bridges, which would be this section right here that's essentially printed over nothing, but is connected on either side to the print still. And then you have overhangs, which would be this section here, which is printed over nothing, and generally requires the supports, which is this green section, to help keep it from drooping, basically, because you can't print over nothing. It's essentially just a hot glue gun, and so that plastic is just going to droop if you try to print over nothing. Yeah. All right. We go for general design features. So we're going to start with bevels. Bevels refers to generally fillets or chamfers. In this case, the fillet is rounding over of your edges and corners versus a chamfer being a flat cut of your edges and corners. Each of them has their orientation strengths and weaknesses. So for the fillets, you can kind of see on these ones that run parallel to the edge, like the build plate of the printer, that you get a little bit of that stair-stepping effect, versus the edge for the vertical edges. You get a nice smooth curve. And then kind of the same here for the chamfers. These horizontal edges are much sharper than the vertical edges that kind of start to get smoothed out by the printer movement and extrusion. One thing you can do is you can kind of combine the chamfers and fillets to get a much smoother transition on the curve. So for the sections of the curve that get close to parallel to the build plate, you can kind of cut the bottom just a little bit with a flat surface. And this allows you can see here that this number 1 is a full fillet section. And even as the full fillet, it kind of doesn't actually make it to the edge of the actual print, because again, you're having that layer stepping of trying to approximate a curve with straight lines. And even just adding a small, like 15-degree angle improves the quality of that surface finish right there. Surfaces. So for curved surfaces, the orientation has a much higher impact on the surface quality. So it's kind of hard to see on the television here, but this print was printed vertically on the build plate, and this print was printed horizontally on the build plate. And you can see that the surface quality is there's a lot more of that layer stepping with the surface finish here. And that's, again, just the trying to approximate a curve with straight lines. You can also find that if you really, really need smooth curved surfaces, step files, some slicers are compatible with step files and will generally give you a better curve surface, since step files are a mathematical definition of a surface as opposed to an approximation of a surface that an STL usually is. Again, it's hard to see, but there's a little bit of a wavy pattern on the surface there. That's vertical fine artifacts. So if you have curved surfaces, some printers are not as good at getting that really nice smooth curve and might have some straight line approximations or little wavy pattern. And then at the very top of the domes, you can sometimes run into gaps in the top surface due to the perimeters not overlapping fully. So increasing perimeters can help with domed surfaces in terms of avoiding those gaps. And then for flat surfaces, you pretty much want them perfectly parallel to the build plate or roughly vertical. As you start to get to like shallower angles, you really get that stair-stepping effect on the surfaces. For holes, is a very common feature in things. Almost every object has one. You often, if you have holes in a horizontal surface of a print, so this print was printed vertically like this, you can see that the top of this arc starts to droop, and then also at the bottom you get this kind of flat approximation again of the curve. And ways that you can avoid the drooping and ensure that you actually have a full circle is to kind of add this teardrop shape. You can play around with the angle and see what works best for your models. And this is just a comparison with a circle printed flat on the build plate. And then for holes, if you have something that you need to print over nothing, you can actually do a bridged layers. So in this case, it's a little bit hard to see. Again, I have all of these 3D prints at the 3D printing station over in the corner over there, so you can come look at them afterwards. But I approximate the circle by having straight lines bridged across. So in this case, we have one layer that passes straight this direction, another layer that passes straight this direction, and then a third layer that passes straight this direction. This makes it so that when the actual circle is printed, it has enough contact points to print correctly, and you don't need any supports on this. Um, Generally, you try to avoid supports because removing them can be a giant pain, and sometimes they just completely fuse to your part, um, as we'll see in a subsequent slide. The other option that you have for holes is doing a full sacrificial layer. So just one layer thick, you close the hole, and then afterwards you can either cut this out with a hobby knife, or if it's something like a screw hole, you can just punch the screw straight through. Both of them make it so that you can see it's a very clean printed hole. Mating surfaces. One thing to watch out for is 3D printers are not super high precision. You shouldn't be expecting, like a CNC mill type results. Reliably on printers, you can go about 2.1 millimeter gap between pieces. And even that still usually requires a pretty well-tuned printer. So we have over here is kind of an example of a test print that you can do. So this prints all in one piece and has a slightly different size gap between each of these segments. And in this case, the 0.1 and the 0.15 don't move at all. They're completely fused into this print. And the 0.2 ended up, I had to use a pair of pliers to snap it loose, but once it was snapped loose, it was able to move. So you can print one of these and figure out what your printer is able to do. And then, yeah, this is kind of general rule of thumb. 0.3 millimeter gap between pieces works for almost all printers. And then a 0.5 millimeter gap or larger works on everything. And then one thing to note is that these tolerances can vary between a horizontal and vertical printed, something like a hole. So in this case, this gap might be different from if this same piece was printed rotated 90 degrees from how it is. So like if it was printed on this side instead. Yeah, threads and fasters. Small threads don't print well. I don't recommend trying to model them and print them. It's usually much better to use some other part that has better manufacturing tolerances, like these little brass heat set inserts here, something like a nut, or just directly screwing into the plastic. These little heat set inserts are great. You just use a soldering iron to heat them up and melt them into a hole in the surface of your plastic. And they generally are stronger than any other option. Usually your part will break before they get pulled out of the print. So then for larger threads, you can model them and they do print great. A couple caveats are you don't want a really sharp profile to the edge of your thread. It's generally best to just cut it flat or round it off to get a better print result. And then one thing that you can do, due to the layer lines being the highest rate of failure for prints, instead of printing them upright, you can actually just slice a side off of the bolt and lay it flat on your build plate. And then you gain the print strength from the layer lines going through circularly through the orientation of the print. And it functions exactly the same, and you gain way more strength that way. And then again, pay attention to your offsets. If you don't add any offset, the two parts are not going to mate at all. Yeah, so here's this example of some supports that I was trying to remove, and they completely fused to the print. It was sort of perfect for the demonstration of why you want to avoid supports. In general, any time you have an overhang that's at 45 degrees or larger, your print should do perfectly fine without any supports. As you kind of get below that, you vary a little bit and might need supports. So you can see here, this surface is 45 and then drops by 10 to 35, 25, 15, and then 0. And as you get kind of into this like 15, 20 range, you can see the surface quality starts to deteriorate without supports. Yes, and then overhangs with sharp corners. As there's less supporting the piece as it's trying to print, the plastic kind of tries to stick to the print head as it moves, and so those really sharp corners can lift up and usually cause print failures by the tool head will then collide with that later and knock your print off the build plate. Yeah, for thin and small features, you can run into a number of issues. Layer orientation is especially critical as you have less material to keep things held together. So something like this piece that's really skinny with the layer lines running this orientation, this would almost definitely snap pretty much immediately, versus if you were able to orient your print so that the lines run through in a more circular throughout the entirety of that piece. You generally want your thin walls to be a multiple of whatever your layer height or perimeter width is, and that just helps with consistent extrusion rates throughout that part of the print, and it helps with strength. Super small details can be kind of like smoothed out or just lost by the tool head doesn't have super high resolution. In this case, this has 6 little walls, but in the model there's actually 7, and it just the 7th one is 0.1 millimeters, and the slicer just completely ignores it altogether and doesn't try to print it. You can also thinner sections. So like this little spring, this is all printed in one piece, and it will flex a little bit. So you can use that to your advantage of, if you want to make some snap fit parts. Again, this orientation for like a little tab, if you had a box that you were going to make with a little flexing tab, you would try to do something a little bit more like this, where you still have, there's a little tiny gap here at the bottom, and it's still connected on either side, but since you have the gap, it's able to flex a little bit and has significantly more strength than just a little tiny tab that sticks out from the top. Yeah, now we move on to some of the stuff that basically only 3D printers can do. So a wonderful thing about the prints being built up layer by layer is that you can actually embed other parts into a 3D print. So a really common thing that I've seen is magnets or something like a nut. So in this case, you can see I have a little hexagon shape to drop a nut into this print. And you can do that by setting a pause at the last layer before that item would be covered up. You really want to make sure that your object is at the print layer, that you're like the height of the print layer you're on, or below. Otherwise, your print head will collide with whatever the object is as it tries to resume. You can see this is the final bridging layer that would trap the part within here. And then the same thing here. This is a horizontally printed, and then vertically. You do need to make sure, so in this case, the walls are just straight after halfway through the bolt, because you still need to be able to drop the bolt all the way into that hole, and having the complete shape of the bolt would interfere with that. Yeah. One thing to watch out for, especially if you're doing magnets, is parts of your print head can be magnetic. And so if you don't glue the piece into your print, it can get pulled out as the print resumes. Or you can have, if you tried to do something like fill a print with sand, there's a cooling fan on the tool head that will start to blow that sand all over the place if you were trying to do something like that. Similar to embedding objects, you can have print in place, which is, again, this object is all printed as one object, but parts can move after you've finished printing. And so if you have parts that loop through each other, they'll be able to move after the print finishes. The one thing you need to make sure to watch out for is that you want each individual part of the object, so in this case, each of these little tabs and then the centerpiece, they all are printed on the build plate or are connected to the build plate in some way. Because if you don't have some kind of way that they're adhered, that piece will start to move around and you'll have print failures. I found that most of the time the tolerances need to be just a little bit larger for print in place versus two parts printed separately that go joined together. Yeah, we have complex structures. This is kind of where your imagination is your limit. You know, you have many complex shapes that are not possible to do through something like injection molding. So you can see here there's tons of internal cavities, lots of spaces where it would be like with a rigid mold, you wouldn't be able to pull that apart without destroying the piece in that. So 3D printing is awesome for that. You do have to still watch out for, you know, those overhangs and other sections. So like this little tiny bit on the skull actually drooped a little bit because I missed putting supports there. And so that's one thing to watch out for. And then this is a little bit more of a slicer hack than anything else. But instead of taking the time to model something like a mesh, you can use the infill patterns and just set top and bottom layers to 0 in the slicer, and then you get the exposed infill pattern as a mesh. It's great for something like if you build a computer case and want to have a fan intake or outtake, you don't have to model that. Finally, we have part strength. In general, increasing the number of parameters increases your part strength, and in terms of strength to weight ratio, significantly more than infill does. I generally don't ever print above like 25% infill. I just up the number of parameters. Most of the time I print at like 10 to 15% infill. In general, higher temp and slower print speeds are better for layer adhesion, but there's kind of a curve of if you go too hot, you basically degrade the material as it's printing and end up with worse results in the end. And then, as I've kept reiterating, print orientation is the most important. So if you have particular axes that needs to have tensile strength, make sure that that is matching the layer lines as opposed to going with the layer lines so it doesn't separate. Glass-filled and carbon fiber materials are often touted as making prints stronger. That's kind of a misnomer or like misguided a little bit. It's more that it increases part stiffness and dimensional stability, but you still are, that layer line is still your weakness, as those carbon fiber particles are not being able to lock and create strength between the layers of the print. Yeah, that's everything. Here's my contact information. Feel free to reach out to me and definitely come chat with me at the 3D printing booth if you would like to. Does anybody have any questions? Yes. I don't know. What was the last section? Sorry. Yes. Okay. So this is mostly talking about FDM, but the techniques apply to most types of printing. And the question is related to basically heating the print afterwards to do something called an annealing process. You definitely can do that. Annealing is you basically bake your part at a specific temperature for a specific set time. What those times are varies between the materials, but you do have to worry about supporting the part during the annealing process. As you heat it up, it will start to deform unless you have some kind of shape or form for it to sit in. So you can actually go There's the person that has the 3D printed violins. They do an annealing process for that, and they have special forms that they put their prints in to maintain the shape during the annealing process. Yes. Yeah, so for these bridge layers, I'm usually doing this in the CAD software itself and not in the slicer. I actually just learned yesterday that FreeCAD is supposed to have a little workbench or plugin that will automatically do this for you. I haven't used it yet, so I can't say how good it is. But yeah, I'm generally modeling that into the part itself. That's correct. Yes, I am taking into account the layer height that I know that I'm going to print at as part of that process. Yeah. Yes. Uh, yes. So metal infused filaments are generally weaker than other filaments. Um, I'm not entirely certain the process behind why that is, but I assume it has to do with the fact that you're sort of reducing the number of like plastic chain bonds within the plastic itself by interrupting that with particles of metal. Um, and I usually it's a very fine metal powder as opposed to like carbon fiber and glass is trying to use like chopped strands. So there's a little bit of length to them that helps add strength. Yes. I've used a bunch of different ones. They all have their quirks. Currently, I've been using Fusion the most. I've also used, and I taught myself CAD using FreeCAD, which is free and open source, which is great. Um, there's a newer piece of software called Plasticity that's not CAD, but it's kind of in between Blender and traditional CAD software. So some people like it more who like if you have experience with Blender or those types of tools, it can be a little bit easier to use than traditional CAD. Yes. Yep. Just a little bit. I've found that there's a couple different techniques. Materials like TPU bond across layers actually really, really well, and usually are watertight. Increasing perimeters can help with making something more watertight because there's less chances of gaps between the layers. Increasing flow rate, maybe even like over extruding a little bit so that the plastic gets extra squished as it's getting put down, can help with water tightness. And then you can also finish with like an epoxy or some kind of resin coating to an object. Yes. I've been using currently Orca Slicer the most. Um, it's it's pretty great. It works with, I have a number of different types of printers and it works with all of them. Um, it has some pretty awesome capabilities. Yeah. Yes. Yeah, the brick stacking. I tried to use the plugin that I found somebody had published maybe like 3 or 4 months ago. And at that time, the model it generated was just all the lines on one layer. So it didn't work how I expected it to. There's been some improvements in the last month or two that are supposed to make it easier to use, but I haven't played around with it yet. And for reference, the brick stacking is normally layer lines are like all run parallel to each other, but the brick stacking kind of overlaps every other perimeter. so that they kind of are offset, and it helps with adhesion, layer adhesion. Yes. Yeah, okay. So they're asking about being able to, if you have a bunch of very thin prints, being able to stack them all into one print and pull them apart afterwards. There's a couple techniques that you can do. I don't think any of the slicers have something built in for that currently. Um, I've seen it done once or twice. Either you can just have a very small gap between each of the pieces so that they don't adhere quite as thoroughly. You can also use something like a PVA support material, so a slightly different material if you have access to two different materials in a print, as like an inner artificial layer between the two that you then pull apart. Um, I've also seen Sharpie used on prints. So if you want to keep two pieces from sticking to each other, like on the top of a support layer, you can actually put a layer of just draw on it with a Sharpie essentially, and it will prevent the pieces from fusing to each other. Yeah, so you would do a pause and then put some Sharpie in the section and then resume the print between each layer. Yeah. All right. Thank you so much for coming.